Dear student, you are watching this video because you are in a mathematical logics course, and today we meet in this format just like in a video lecture. Next week I hope we will meet as regular in our online meeting in Zoom. Okay, we will proceed to the lecture and we will start from the homework. Okay, let's start from the homework we had for this week. This was a puzzle entitled like Whose Fault? And we have 5 actors. 4 of them are under suspicion, and we have an inspector who is investigating somehow of some of event. And mechanic, watchmaker, sailor, and aristocrat are those 4 persons who are giving some evidence regarding that event. As you remember, we had something like testimonies saying that that is sailor whose fault. Another was that is a aristocrat. Another said that watchmaker actually said that was not he, so that was not me. Yeah, and a aristocrat gave a testimony like saying that the sailor is lying, saying that was me. Okay, and after additional investigation, our inspector got a knowledge that only one of those said truth. So, whose fault? Yeah, that was a homework. Okay, so we had some testimonies and persons who are in the investigation, and inspector who asked for those testimonies. So the results what that the inspector collected are as so. Mechanic said that was a sailor's fault. Yeah. Then the sailor said that was a aristocrat's fault. The watchmaker said that was not he, yeah, not watchmaker. And the aristocrat said that the sailor is lying, saying that was me. So actually he's claiming that was not he, not aristocrat. So we get these 4 statements. That should be how to say, could be like either is that is or sailor or aristocrat or not watchmaker or not aristocrat. Yeah. After some additional investigation, inspector got knowledge that only one said true. That's why we can say that this formula must evaluate to true, to always true formula. Yeah. What can we see in this formula? From the logical laws and Boolean algebra laws, we already should know that if we have some formula like saying like we have B or not B, so we know that this structure will evaluate to always true. Its formula is always true. Why? You can just try like this. You take a statement B, and as a logical statement, it can be either false, either true. Yeah. So, and when we connect by disjunction, so we apply a disjunction law, and we get like we will be connecting statement B with a inverted B. This means with the column of 1 and 0. Yeah. And as a result, we will get, so we take disjunction 0, disjunction 1. So if one of the operands is 1, we get 1. Yeah. And again, we take 1 and 0 by disjunction, so the result will be 1. That's why, so we got a column of 1s. So that's why we say that such a formulas having a statement and an opposite statement, they are and connected with disjunction, so they always are true. And if we take an eye careful, and we see that we have a statement saying that is a aristocrat fault, and another statement saying that that was not an aristocrat. So this means that in this formula, those two statements, A and not A, connected by disjunction, they will give that one. Yeah. So either A is true, either not A is true. Yeah. One of them is true. That means that all others, sailor and not watchmaker, should be true in opposite. So they are false. So we invert them and get that that was not sailor, but by negating watchmaker, we get that that was a watchmaker's fault. So an answer is to the question whose fault, an answer is watchmaker. Yeah, watchmaker. That's it for the homework. Now let's spend some time on Boolean operators and their truth tables, as this is a multiplication table for logics. Yeah, we have multiplication table in arithmetics, and for logics we have as well. So we already know that there are Boolean operators such as negation, conjunction, disjunction, implication, equivalence, exclusive, or when we have NAND, and NOR. Yeah. So let's have two logical operands A and B, and let's draw the truth tables for all of the operators we mentioned here. Okay, so if we have two operands, so by default they can be true or false, so two values, and two operators, 2 in the power of 2, we get 4 interpretations. Yeah. So that's why we draw here all possible combinations of 0 and 1, or true or false. So 0 is for false and 1 for true. So we both can be false, one of them can be true, another one can be true, and both can be true. So if we have a negated A, we invert the column A. So we will get like 1, 1, 0, 0. If we have negated B, so we will get inverted the column B. So we, as a result, we write 1, 0, 1, 0. Yeah, we simply invert the initial columns. Okay, now let's draw the truth column for conjunction. So if we have a conjunction B, so the result will be, according to the conjunction law, the result will be true only both operands are true. So in the line where both are true, yeah, we get result 1. Other lines are with zeros. Yeah? So this is conjunction. For disjunction, operation OR, so we get false in only one line when both operands are false. So here we have false, and here we have true. Yeah. So disjunction also stands for operation OR. We can call it OR, and conjunction stands for operator AND. You can call it AND. Yeah. So negation, also known like not. Yeah. Okay. Let's continue, and now let's draw a column for implication. Yeah. A implication to B. The law of implication says that result of implication from A to B will result into false in the case when we have a true premise and a false conclusion. So actually this is the line here. Yeah? So in this line implication is false, and in other lines we have 1. This is a law, a rule how this operator behaves. Yeah. Okay. And now let's draw for equivalence. For equivalence, it says that we take we get true when the operands values match. So actually this is the case in this line and this line. Yeah, in this case they match both zeros or both ones. So that's why equivalence is 1 here and 1 here, and 0 is here. Okay. As well, we already know that exclusive OR, this one, yeah, is an opposite to the equivalence. So that's why the law of exclusive OR takes out the line with both ones. Yeah, this line will be false. Yeah, in this case, and the truth result is true only when values of operands differ. Yeah, differ. Okay. And the rest is for negated and negated OR. So NAND actually is inverted conjunction. Yeah, so we get 0 here, ones here, and NOR, negated or negated disjunction, we get values inverted in this column. We get 1, 0, 0, 0. Yeah. So that are the truth tables for all Boolean operators we could be using. And actually, you need to learn the rules who assign how these operators behave. Yeah, this is very essential knowledge. Okay, next important thing I want to talk about is logically equivalent formulas. And in Boolean algebra, we have to remember some important rules that help us to make computations. So let's have a look and to the rules that help us to absorb some constants if we have in a formula. For example, like here, so if we have a disjunction of some formula with a true value, the resulting formula will be simply true. Yeah. If we have the same disjunction but with the false constant, or the formula that is always false, so we will obtain as a result the previous formula A. So if we have an implication from some formula to true, so we get true. Yeah. If we have an implication to false, so we will get not A. Yeah, and so on. Yeah. So actually, these are also important here and here. Yeah. So we have to learn these formulas like logical equivalences to make our computations faster than we do it on a paper. Yeah, and here as well. Yeah? So these are formulas showing us. Sorry. Yeah. Showing up as a absorption of constants. Next important thing is so-called identical operands. And the collapsing can also occur when both operands of an operator are the same, or one is the negation of another. Yeah, so we have to remember that the double negation results into a simple statement. If we have a if we have conjunction of the same operands, so we write it only once. Yeah, only once. We have this disjunction if statement and this the same negated statement, so we will get true as a result. We have true, or simply we write 1, yeah, true. If we have implication from the same statement to the same, we get true. If we have equivalence like this, so again we have true. And to write a negation of a statement A, we can do like just putting a NAND with A, this is a negation, or as well we can have the same negation by writing A nor A. Yeah. So if we have a statement, same statement in disjunction, A disjunction A, so it's enough to write once. Yeah, we have simply A. If we have a conjunction with the statement A and negated A, so the result will be false, and a exclusive OR with the same statement will result into false. Yeah, so these are also equivalent formulas to remember and to apply them when we do a logical computation. In Boolean algebra, we also have laws of commutativity, associativity, and distributivity. But not all operators are used to fulfill these requirements. Yeah. But those who are here can be used in the manner you see. So it means that if we have A or B, this will be the same to write B or A as well. If we have A and B, it's the same to write B and A. So we can change the positions. Yeah. The same holds for equivalence, for exclusive OR, for negated AND and negated OR. Yeah. So actually implication is not the one who can be written in such a way, but we have another equivalent formula saying that for implication that we can write, if we have A implication B, this will be the same as writing not B implication to not A in a negated form. Yeah. Again, actually this formula is a contrapositive to the initial one. Yeah. So disjunction, conjunction, equivalence and non-equivalence are associative. Yeah, so we can do like changing the order of operation if the same operator stands. It doesn't matter if we first connect B or C, or first connect A and B and then after C. The result will be the same. The same stands for equivalence, yeah, conjunction and exclusive OR, but not for the implication. Implication is not associative. Yeah. Okay. And disjunction and conjunction are distributive over each other. This means that we can open the parentheses by putting disjunction into pair of another operand and connect the parentheses by help of this conjunction here. And the same stands for disjunction in the brackets and conjunction outside. So this is a distribute law. Okay. As well, operators can be defined by using each other. These are important equivalent formulas that also requires to be remembered or at least written down to have on your side to help you when you do a computation. Okay, and at least to remember are formulas that define so-called Morgan's laws. So these are rules showing us how to do disjunction with negation and conjunction, yeah, and conjunction with the help of negation and disjunction. Okay. Okay, so be careful and read. For this week, you have to read the whole chapter 2, yeah, from start to the end. And now I will show you some tricks how to write down the formula expressed in main operators if you have a logical, if you have a truth table of the logical formula. Let's take the truth table of exclusive OR, and we will write down the formula from the table. Yeah. So let's have like this. And we know that exclusive OR gives true when the operand values differ, and when they match, we have false. To write down the formula, we have to have some knowledge about so-called algebraic notation of writing formulas. So this formula can be written as well like formula from a b expressed as a sum of so-called min terms, values 1, 2, 1, 2. This means that we take care about the interpretations that are true. Min terms mean that we take care about the interpretations that evaluate to true. So the lines are 1 and 2. The count comes from this line is 0, this one 1, 2, 3. So we count from 0 to 3. And actually these lines correspond to binary notation of a decimal number. So decimal 0, this is decimal 0 is a binary code of 0, 0. Decimal 1 is a binary code of 0, 1. Decimal 2 has a binary code 1, 0. Decimal 3 has a binary code 1, 1. Actually, the truth table, if we write interpretations from the smallest to the largest, they match to the decimal numbers from 0 to 3 in a case when we have two logical operands. And this type of notation is like a so-called algebraic notation and is used as a sum of min terms, and we show which lines evaluate to true in that formula. So we say these ones, yeah, these are, yeah. So actually these two lines define the formula, and we can extract the formula from this truth table. So to do this, we continue according to the rules. So we take into notice line 1 and 2, 1 and 2, yeah, and now write the operands according to their truth value in the interpretation. So for A, we have a 0. That's why we write it like not A. Yeah? In between columns, we take as it would be a conjunction. Yeah? So we write conjunction with, here we have 1, so we write like B. We take B as it is. In between lines, we consider as a disjunction, so that's why we take disjunction, and we will write, we take A, it's 1 here, so we take A as it is, and now conjunction, conjunction, and we have here 0 for B, so that's why we write not B. So, and this is a Boolean formula expressed with the use of the main operators. Main are negation, conjunction, and disjunction. And we have now two logical equivalent formulas, as we can express exclusive OR, yeah, with the help of conjunction, disjunction, and negation, like here. Yeah, this is the same logical phenomenon here. This is an example how can we write a formula having a truth table. Okay. Now your homework number 3. So imagine we are in a sports club, and that club has a very strange rules. One of the rules says that members of a volleyball group must also attend the swimming group. Second rule says that you cannot be a member of a chess group and a member of a swimming group at the same time if you are not a member of a volleyball group. And the third rule says that no member of a chess club may be a member of a volleyball group. Okay, so club is the same as group, to notice. And the question is now, how can we simplify these rules to get it more clear? You need to help students to get an answer to a question. What groups can be attended, let's say, together? And to solve this, you need to write those statements as a logical formula. Each statement is a formula, and then you connect them together and try apply the Boolean laws you already know in order to simplify the whole formula you got, to simplify it to the very small and tiny look, which will help us to say these long rules in a very short and nice way. So this is your homework for the next week. As well, the reading of chapter 2. Okay,